The purpose of this lab was to see how, in the absence of air resistance, free-falling bodies are great examples of one-dimensional motion with constant acceleration. In this lab, we specifically used air-powered projectiles or rockets to determine the maximum height, time of flight, initial and final velocities, and to also examine how these quantities change over time and how they depend upon the initial conditions. In order to collect data for this lab, we used digital video instead of traditional methods in order to capture the motion of our projectiles. We also used the frame rate from the videos in our calculations in order to determine some of the rocket's factors. Some materials you need for the lab are an air rocket, a bicycle pump, a meter stick, a digital phone, and a laptop. Another thing to take into consideration is to not lean over the rockets while launching, because then when the rocket goes, it will launch right into your face, which is not fun. And rockets should only be launched vertically into the sky because you do not need angles unless you're Aiden and you want to launch the rocket at me, and in that case it is perfectly acceptable.
Be sure to look out for artificial
Ow!
Alright, so to start we have the cap. Put it on like this. Make sure it clicks. Then you have the body of the rocket. Put it on. Home. Put it on top. Make sure it's tight. Then you have the pump. Gotta make sure it's coming out the right hole. Oh wait, there's only one hole on this one. Then you put the pump on it. And open that thing up so it stays tight. And then pump until it goes up. Oh my god.
Oh, that went really high.
That was the highest one.
Yeah. Go when you're ready.
Normally there would be about 2 or 3 times the amount of trials that we actually have in this lab, but due to the software I'm using and the iPhone to Windows conversion, I guess, all the slow-mo videos I took on my iPhone ended up being about 15 minutes long on Windows and couldn't convert correctly, so I only have in this lab the normal speed videos, but all the slow ones we still did use for calculations, even though I'm not showing them in this video lab.
Alright, so in the first frame it moved 23 centimeters, and each frame it's 240 frames per second, so that was 1 divided by 240 seconds, and then you convert it, it becomes 0.23 meters, and 1 divided by 240 seconds. V equals D over T, so it's V equals 0.23 over 1 over 240. That's the velocity plus or minus the uncertainty. And we got the uncertainty from this. Take the percent of that, and then multiply that percent by this. And that's how we got that. Then we use this equation to get delta y. V squared equals V naught squared plus 2a delta y. So at the top it's not going to be moving, so it's going to be 0 meters per second. And then that's the initial. That's gravity.
Go.
We did the same thing as last time, but with different numbers.
For the purposes of this lab, we did not take into account air resistance when doing the calculations in order to truly see the effects of one-dimensional motion. Another thing about our calculations is that the results are way higher than what they're supposed to be, and that's due to the fact that we didn't do the frame rate exactly right, and also the rocket that we had was actually broken, and it took about 20 pumps in order to get into the air. So by, that amount of pumps, it went way higher than it was supposed to when you're looking at like anyone else's group. So for those reasons, our lab results are definitely way off, and are definitely skewed, definitely more than everyone else's. But other than that, the procedure of the lab was a success, but I feel like if we had different equipment, then we probably would have gotten more accurate results. And if we tended to use the regular speed of the camera instead of the enhanced or the slow motion, then we probably would have gotten more accurate results overall.